Should I start? Okay. So, in the morning we saw that we can in fact write a potential which is 4D gravity scalar potential for the moduli fields when we have non-zero fluxes, and it was given by this expression where I and J were running over all moduli fields. That means the Kähler moduli and the complex structure moduli and the dilaton. Now, we had kind of fixed the dilaton and the complex structure moduli. So, let me just write them, this DIW0, and that fixes the CS moduli and the dilaton, where the dilaton, the inverse of the imaginary part of the dilaton is basically the string coupling, and this will kind of fix W to some constant value W0, which is given by the Weber basically after stabilizing the complex structure moduli. But I told that in that case, even after turning on the fluxes, we couldn't fix the Kähler moduli. So, let me just tell you why. So, I am kind of only writing the Kähler potential, which contributes to the potential, this scalar potential of Kähler moduli. So, I am kind of not writing the complex structure part and the dilaton part. And after fixing the complex structure moduli and dilaton, we have W set to some W0. So, when we compute this scalar potential for these moduli, which are, you can call Kähler moduli or the volume moduli, because they are kind of given by the volume of the Calabi-Yau. So, dA will be this, and let's assume that we have only one Kähler moduli. So, H11 is 1. In that case, this volume is given by something like T bar to the power 3 by 2. So, using that, we can compute this dTW, which will be basically minus 3 T plus T bar, and that will be basically same for this T bar as well, because it's symmetric in T and T bar. And I think I forgot to tell one thing. So, this K, I, J are basically inverse of what we call Kähler metric, which is a metric on the moduli space. So, K, I, J bar lower indices will be given as del I, del J bar of the Kähler potential. Okay. So, in case of this single Kähler moduli, this inverse, which is now KT T bar, will be this T plus T bar square over 3. Now, we can substitute this calculation into the expression for the full scalar potential, and what we will get is basically we have a 0 potential for the Kähler moduli at tree level. So, everything we have done so far, we have done at tree level. So, when we substitute it there, what we get is basically e to the power k, and then minus 3 this dt bar whole square times this the Kähler metric. Okay, this there will be a W0 sitting here because of, and divide by 3, and then we will have mod W0 square. In our case, I am assuming that it is kind of real, and then we will have this 3 thing. So this will basically cancel out with that 3 mod W0 square. So this property of basically cancelling out all Kähler moduli dependent terms at tree level is what we call no scale structure or no scale property, and the statement is kind of equivalent because I mean it is saying that this inverse Kähler metric times this del A k and del B bar k is equal to 3, and this is always satisfied for the Calabi-Yau. Okay. So in order to stabilize the volume moduli, so I will call the Kähler moduli volume moduli from now on, we need to kind of go to maybe next order in theory. So there are basically two ways in which we can have a potential for the this volume moduli. Well, first one is called KKLT and the second one is called LVS. Is it okay? I mean, is it fast or slow?
Can you repeat this once more? Like, so you have 3 moduli fields, which is
3 types of moduli fields.
In
Yes.
terms of these variables, you are saying that the Kähler potential goes as some volume form.
Yes. So the total Kähler potential I had written was this K, which was minus twice of volume minus log of minus I tau plus tau minus tau bar, which was the dilaton part, and then I had log of this I times integral this omega wedge omega bar, and we saw that this is kind of function of z, so it is dependent on the complex structure. Okay.
And then you're setting those to 0, is it? Like,
So I am kind of I have integrated them out, and that is the fact that I have set W to some W0.
okay.
So after that, we are only left with this part of the Kähler potential, and with one Kähler moduli, it looks like that. Okay. So the first one, first model is called KKLT model, that is short for Kacheru-Galloway, Linde and Trivedi. And what the idea of this model is that we take some non-perturbative effect, which is usually generated by some D3 or D7 kind of branes, and when you take that, you can have 2 different types of terms coming in your Kähler potential, one in Kähler potential and other in your super potential. So it's something like K0, which means tree level, then some function, let's say A1, e to the power minus 8t, and the second one will be W, which will be given as some wave of it times some A2 e to the power minus 8t. Okay. So we will only be looking at these kind of non-perturbative corrections. Both are kind of equivalent, only different thing is that how much, I mean, what kind of, geometry you are taking. Depending on what kind of geometry you are taking, you can get either this or that. So let me just
By geometry, you mean the Calabi
the
geometry?
nahi, warping. I mean the warping, what type of?
Oh, you mean the de-Bruijn warping?
Yeah, yeah. Okay. So we have for KKLT, W is given by this some A times e to the power minus kt, and these will be dependent on how these non-perturbative corrections are coming in. Okay. So when we substitute this into the scalar potential, so let me just go back to this. Just a second. Yeah. So when we substitute that in, our scalar potential and set the imaginary part of this t to be 0, it is just for simplicity, it can be fixed separately. So it is fixed at some value, let's say that it is 0 here. Then the KKLT scalar potential for the Kähler moduli will look something like this. So e to the power minus 2a sigma small a square capital A square divided by 3 times volume to the power 2/3 times some term here, then there is a minus term coming from by 3, and everything is kind of multiplied by string coupling, factor of string coupling. Okay. So when we kind of minimize this potential with respect to this sigma, so sorry, this will be sigma and this will also be sigma.
Maybe I missed something. I thought
Yeah.
if you just said W to anything and the tau to 0, I thought you always get V 0 from your previous calculation. Is that not correct?
No, we set W to some constant value, which was kind of vacuum expectation value after stabilizing the other moduli. And there was no t dependent term coming in W, right?
But even if it did, won't this equation still be true? Even if W depended
No,
on
no,
t?
because this equation is kind of consequence of this thing.
Okay.
And in case of when the W is constant, we only have this term coming, right? Otherwise, we'll have when we take this dAW, there will be a del AW term also.
I see. Okay.
So when we only have this, then it is cancelling. I mean, that will always cancel, but the other term will be non-zero. Okay. So when we stabilize or minimize this potential, we get a relation which is this tau is kind of fixed at logarithmically in this W0. So if I take mod, then it will be plus, because taus are kind of volumes, sorry, again it's sigma. So sigmas are kind of volumes of the 4 cycles, so they have to be positive. Okay, and this is coming from a relation. So it is kind of, let me just write, the minima is at some Now going from here to there, what we have assumed is that this A times sigma should be much larger than 1, and that is kind of assumption for that this only one instanton correction will be kind of enough. So that is the assumption that we are taking. So the drawback, or maybe the constraint that KKLT models have, is that this W0 should be very small. Okay, but these are very rare occurrences in string landscape. So nobody was kind of able to construct explicit model where W0 is very small until recently, I think in 2019. I'm forgetting the authors, but I don't know, it was some 1912 10047, something like that. So there what they did, so let me just tell a little bit about that, because
Can you also ask, so my layman understanding of KKT, I thought they had a de Sitter compactification. I mean, you got the background geometry to be de Sitter or something, right?
yeah, so okay. So right now when I substitute the minimum of the tau in the this, so we'll get a ADS. But then we can uplift that using a term like some rho over sigma cube, okay, and that uplift will give us de Sitter vacuum.
But in the entire construction, one of the requirement was that we needed Poincare, and somehow these things are no longer true. Where did that break?
No, that is fine, but I mean the main aim was kind of to stabilize the Kähler moduli, right?
Right, but I thought the KKLT, again, layman understanding that I thought KKLT showed that you could have a de Sitter spacetime as your, after you compactify, you get a de Sitter spacetime as opposed to flat or ADS or something like that.
Yes, but only after including such corrections. So it is subleading to that correction as well. So if I include this correction, then this 3/2 will become something like 5/2 something. So yeah.
So your eta mu gets corrected to something that gives you de Sitter or something like that, is it? So like when you split the initial metric, this GM,
Yeah.
you had the eta mu plus G small m, and then you said that you want this eta mu to be Poincare invariant, the Minkowski metric.
Yes.
But now once you compactify, is there a way to get something other than eta mu? Like if I want, let's say, de Sitter there.
Okay. So you are saying some. I mean, yeah, it is kind of equivalent to saying that, but I don't have like direct, thing. But one thing is that the warping we had earlier with associated, this eta mu, this will also get some fixed value. So it will be like e to the power minus, plus some pi factors times some k by m, where these are the, flux quanta kind of thing.
Just to understand, if I started with this eta mu plus this slip,
Yes.
then I do some choose a particular stabilization, etc., and then I somehow that corrects this eta mu to give me de Sitter.
Yes, that is. I mean, yeah, the background metric is always eta mu. Okay, so let me just tell a little bit about this construction where we get W0 to be very small, and so if you remember, after quantizing the fluxes, we could write this W in terms of this flux quanta F tau and then sigma dot pi. This was, you can write it, I didn't write it that time. So sigma was our symplectic metric, which was 0, identity, minus identity 0, and pi is our period vectors which we had earlier. So, and the Kähler, so okay, so one more point is that you need W0 to be very small, and for that you kind of have to fix the other moduli which are the complex structure moduli and tau such that you get it very small, because this is the kind of web after fixing the complex structure moduli. So, this construction is kind of before stabilizing the complex structure moduli. So, we need to write the relevant Kähler potential term. So, this is corresponding to the complex structure moduli, and then as usual we have this dilaton thing. Okay. Now, let me just write one more thing. So, the pi's are kind of given as this BA omega and AA omega, and that I define to be this some GA and not U, ZA. So, if I define it like that, then what happens? Okay, so let me just phrase what I want to say. Yeah. So, in their construction, there is a large complex structure limit, which is always true. So, if you go to large complex structure limit, what you can do is you can write the total superpotential as two terms, which is the first one is some perturbative part and second one is some non-perturbative part, and these are basically given by the derivative of these functions. So, it is given as W is given as MA del A okay, no, not this one, sorry. So, that is different thing. Maybe I will just say that we can split this in these two, which is kind of normal thing. Once you have some large volume limit, you can always have something which is kind of inverse proportional to that and something exponentially negative of the exponential proportional to that. And let us say if we have a basis where we can write our quantized the fluxes in this way. So, I will tell what M, A and B's are. I mean, if you guys are not following, we can go to LBS directly, but just wanted to tell you. So, we have, so let me just recap. So, for KKLT, one requirement is that this W0 should be very small. In order to W0 be small, what we want to do is we want to kind of stabilize our complex structure moduli at such value that it will give W0 to be small enough for KKLT to be in the limit where EFT is in control. So, for that there is this construction where there is a lemma. So, given that we can write these flux quantas in that form, and in large complex structure we can write this perturbative and non-perturbative part separately. these m and k's, they belong to this integer kind of space, where m is nothing but the quanta corresponding to the F3 and k is corresponding to the H3, and they have to satisfy the D3 tadpole condition. So, this m dot k with the minus sign should be less than or equal to this QD3. Then if we can write a matrix which is kind of invertible in such a way that it is this K, A, B, C, MC, where K, A, B, C are the intersection numbers which we got after we wrote the volumes in terms of, the 2 cycles, and the A there is given by half of this. So, I will give an example, maybe then it will be clear, sorry. Okay, so if you can write a metric, then along the direction where these moduli fields z and there exists a vector, if we can write in terms of this, where P is a kind of vector given in terms of this matrix n. So, it is like this. So, given that we have the flux quanta and they satisfy this D3 charge condition, if we can define a matrix which is kind of given in terms of this quanta and the intersection number of the Calabi-Yau, then we can have these p vectors along that vector. If we take our complex structure whole manifold to be, then what will happen is the perturbative part of the superpotential will vanish and we will only be left with the non-perturbative part, but again in large complex structure limit that will be given as something e to the power minus something times the complex structure, and that will be very small. So, if this is satisfied, then what happens is this W perturbative is kind of 0 and this W effective, which is now only the non-perturbative part, is given as some q vectors times this m dot q divided by some numerical factors times e to the power 2 pi I p dot q. Is that okay? So, for example, if we take an example for what is called CP11169, this is a Calabi-Yau manifold. The intersection numbers are kind of K11 is 9, K112 is 3 and K122 is 1, and these are symmetric in this indices. Then our A is basically given as 1 by 2, 9330, and B is 1 by 4, 17 by 9, 17 by 9. So, by doing this whole thing, what I am trying to emphasize is that getting a very small value of W0 is kind of not easy, and only one construction that exists is this one, but that will also be very, in terms of statistics, it will be very kind of rare. Okay.
Sorry, so this portability part of the superpotential is zero. So what kind of gauge theory it will like correspond to? Usually it is like one loop itself.
I don't know exactly, like.
I mean, it is coming only from the geometry, right?
Yes.
From the gauge.
No. So, okay, I don't have an answer to that right now. So, okay. So, in this specific example, what we will have is this W effective can be written as some constant C times this e to the power 2 pi I P1 tau plus A e to the power 2 pi I is P2 tau, where tau is, our z's are kind of given as tau times this P1 and P2. So I am only taking like two, directions here. And once we do that, and in this case the QD3 charge is 138, and in order to satisfy, when you kind of impose all these conditions, that this has to be integer, this has to satisfy this thing, and then we impose that this is invertible, then what we get is basically two solutions only. So m is minus 16, 50, and k is 3 and minus 4. Now, if we didn't had those constraints, then just to satisfy that QD3 is 138, we could have lots of solutions, right? Because you only have to satisfy this equation basically. So everything that is below this 138, we can have that as a vacuum solution. So, but by imposing this specific condition that the perturbative part of superpotential is 0, and that is via this construction, then we only get like two solutions in this case, and the z's is kind of fixed. So let's say z1 is fixed at 2.74 some this number, and z2 is fixed at 2.057 I, and by substituting this into this form, you can get a number for P, because we know what K ABCs are and what we know what K is. So what we get is basically, for the first solution, what we get is that this W0 after stabilizing this complex structure moduli is 2.037 into 10 to the power minus 8. So that is kind of a desirable number to get our KKLT de Sitter vacuum. Okay, so this was the basically construction given by the original authors, and we also did kind of a numerical analysis for different kind of examples, and what we got is after doing that, it was expected that once you have some large number of QD3, in that case, what will happen is you will have large number of vacua that will give me this W0 which is smaller than 1. But what happened is we, like, even taking, let's say, QD3 to be of order of 500, we got very small numbers. So something like 72 or 38 numbers we got, I mean, of order. So that is kind of not, I mean, statistically significant. And the reason for that is because, see, these Zs are kind of living in this 2H, or at least this H1, 2 plus 1 dimensions. But when you choose it to be around some locus, then it is kind of like very small subspace of the total, space. So that way you can understand why there is such a low number of vacua in, this construction. So far we had only one construction which can give like explicitly low values of W0, but that is also not, good enough. Or even like stronger thing is it's like measure zero in the whole space of solutions.
Is there a relation between how small W should be and the value of the cosmological constant?
Yes.
So smaller W means
Smaller, yes. It's kind of proportional to the square of, W's. Yeah. I mean, there will be also other factors sitting there, but yeah, it is.
So even in this model, it's only 10 to the minus 8 or something.
Yeah, something like that, yes.
So if you want 10 to the minus,
They have constructed a vacuum which was like 10 to the power minus 100 or something. Yeah. So you can. So the statement is that these constructions are kind of like existential proof that you can have a de Sitter with a very small cosmological constant. I mean, it is like what I said, it is like some proof that there exists some, solution. But when you want to do the phenomenology, you want kind of some tuning freedom, right? So for that, it is like not good enough.
But the amount of freedom that we have is
Not good enough, yeah. Because if you remember, we had like some 10 to the power 100 kind of vacua for a given thing. And here you're only getting order 100 things. So it's like in that, set of vacua, it's like nothing. Okay. So that is what I will say about KKLT.
is there a bug or a feature? Like, could they say that it's actually a good thing that from string theory, there's only order 100 of vacuum that I really need to look for, like, rather than 10 to the 5.
Okay, so you are saying like,
It's so rare that, almost all, like, I don't care about it.
but the thing is, I mean, when you go to some realistic examples, like here I have taken only 2 complex structure moduli, let's say. So if you go to some realistic example, there are many issues which comes with it. So I don't know if you can say like only look at only these things and then we'll get what we want. So first thing is how you will stabilize in this construction, how you will be able to stabilize all complex structure moduli given that you have such a heavy constraint on these fluxes. Okay, because you need large number of fluxes so that you can stabilize all moduli simultaneously. But if you put such a constraint, then it is little hard to stabilize all the moduli. And that is kind of in a generic model I am talking about. But yeah, but in simplest case, like if you say that our universe will have only 1 or 2 complex structure, then maybe yes. But then there is a problem of whether this vacuum is actually true vacuum or not. So when you have smaller number of moduli, then there is also some problems. Okay. So the second model of stabilizing this volume moduli are there is something called large volume scenarios, which is LVS. And for this to understand, we'll need at least 2 Kähler moduli. So my volume will look like something tau 3/2. Okay. So just don't confuse it with the tau we write for string dilaton. So it is just the real part of this t's. So real of t I is what I am writing as tau I, and the subscript is kind of to denote that this is big and this is small. Okay. So in LVS model, in addition to the non-perturbative correction to the superpotential, so e to the power minus as ts, and why I am writing only the ts part, because this is very big compared to this one. So let me just write that also. So TB is much larger than TS, such that the volume is only given as this thing. So in that case, the only significant correction from the non-perturbative part will be coming from on the small modulus. Then in this model, we also consider the alpha prime corrections in the Kähler potential. So it is given by 2 gs to the power 3/2. Okay. So where this xi is kind of minus of the Euler number of our Calabi-Yau manifold times some numerical things, so some 2 pi factor sitting here. And this is basically what alpha prime cube corrections, which are kind of corrections related to the r to the power 4. Okay. So when you use these two expressions for the Kähler potential and scalar potential, superpotential, and substitute that into the original potential we had, this V. So in case of LVS, what it looks like is some numerical factors, so I am not writing them, times this square root of tau s e to the power minus as tau s, sorry, this 2, and this volume, again there will be a factor of gs sitting outside, and then we will have this some numerical factors which will be dependent on some as and capital AS here also. So I am just not writing them because it is not relevant that much to the discussion. Volume square, and then we have three times this xi W0 square over 8 volume cube, and one more factor of this G string. Okay. So one thing you can see is in this potential is it is like kind of expansion in inverse power of the volume of the manifold, and that is one reason why we are only taking the alpha prime cube corrections, because when you go to the higher order correction, they will come like this volume some 11/4 or something much bigger, some I don't know, something like that. So that is why we are kind of truncating only to the alpha prime cube corrections. Now, when you stabilize minimize this potential with respect to this tau s, then what will happen is this volume, the vacuum expectation value or the value of the volume at the minima is given as this expression, and where tau s is kind of stabilized in inverse of the string coupling. And if you remember, the volume is kind of given as this tau b. So, this is basically equivalent to some vacuum expectation value of tau b. Now, once you look at this wave of the volume, you can see that it is kind of stabilized at exponentially high values. So, that is why the name comes that large volume scenarios. So, in these scenarios what happens is that after stabilization the volume moduli are stabilized at exponentially large values, and that is kind of self consistent because our potential was in inverse powers of the volume. So, if you are neglecting higher powers, then it is kind of not problematic. I don't know if there is anything else to talk about. Yes.
So, is Calabi-Yau the only way to compactify these additional dimensions, or are there some other ways?
If you want minimal supersymmetry, that is if you start with n is equal to 1, you get n is equal to 1, or n is equal to 2 in type 2b case, get n is equal to 2, then yes.
That is the only.
Yeah, because we want the SU3 holonomy to be there, that and by definition only Calabi-Yaus are the such manifold which are compact, complex and have that SU3.
And how, so the standard argument for them being compact is that we shouldn't be able to detect them or something like that.
Yes.
Is it no other possibility that they can be some extra large that we don't even see them having, like?
I think so far our intuition is like if something is large we can definitely see that.
Definitely.
Yeah. So you can probe that, right, because it's low energy thing.
Yeah, so given the fact that at LHC supersymmetry models have been kind of
Yes.
towards the very verge of getting eliminated, at least the minimal
MSSM.
Yeah.
13.6 up to
14, yeah,
Yeah.
14 TV something.
yeah. So do you think there is non-Calabi-Yau should be in?
Yeah, definitely there can be. I mean, if you don't want supersymmetry, then there is no point of kind of compactifying on Calabi-Yau, right?
Yeah.
We can have any manifold which breaks supersymmetry and we'll get whatever we want.
Oh, so then the analysis will become even more complicated, meaning
Yeah,
you can do anything, right?
yeah. So all other, yeah. I don't know if there are, maybe there are some compact manifolds, I think there should be, that will break kind of all supersymmetries present in superstring theory. I can give kind of definition of what swampland is, but I will not do anything other than that. So today is like kind of compensation for all extra time I took. So the swampland is kind of so the landscape, we saw that what we call landscape is all such 4D effective theories which are coming from some consistent gravity, quantum gravity theory. But the swampland is in like different to that. So the swampland is set of all low energy theories which don't have a consistent quantum gravity completion. So these set of theories are what we call swampland, and so that is why the name is kind of swampland, landscape and swampland. And the conjectures of this theory, so I will not mention the conjectures, I will mention what they are trying to do. So there are lots of conjectures. I don't know if any of them are proven till now, but yeah. So the conjectures are basically kind of creating a border between or this or maybe I should write it as they are kind of specifying the properties which consistent quantum gravity theory should or should not have. So this is what all the conjectures are trying to prove, and yeah, so that is. Sorry, I mean today I couldn't prepare very well, so it was little bit, unprepared. Lamp post is like you pick one vacuum and you try to do everything, around that. So you'll that is the lamp post. That is the lamp post problem actually, because I mean then you will try to kind of manipulate things in a way that you get what we see currently in standard model or beyond standard model, but it might be possible that some other vacuum has already that property, but since you didn't pick that one, you're kind of having a problem or maybe set of problems.
Standard model is a lamp post.
No. Standard model, I don't know what it is. It may be in swampland or landscape. Nobody knows right now. But if you want some quantum gravity, which is some beautiful thing, then I think you should stick to landscape. Good question. Yes, yes.